Okay, I'll now show you some examples of continuous random variables which we have done in class. Of course, we've already discussed discrete random variables. Now, a random variable in general, once again, just something that's producing a number from a chance process. Now, if it has a countable number of outcomes, then we call it a discrete random variable where there's gaps between the values, such as, for people, a discrete random variable would be the number of pets they have. Let's say it could be 0, 1, 2, 3, 4, or so forth, or the number of siblings someone has could be 0, 1, 2, 3, 4. It'd be impossible to have a value between like 1 and 2, like a decimal number. Although you can have something like shoe size that is discrete, that it would contain decimals. So sometimes it can contain decimals, but the key thing is there's gaps between the numbers and there's a countable number of outcomes. With continuous random variables, it's going to be a number that can take any sort of value at an interval, such as people's heights could be 67.286 inches tall, and another person is 59.682 inches tall, or whatever, or people's weights, or how long they slept, like 7.286 hours, or something like that, where it can take any value in an interval. Our most two popular kinds of continuous random variables are uniform and normal. Those are the main two that we deal with. Now, there's almost an indefinite number of different types of distributions out there that we could work with their areas, but these are the two that we care about. Now, it's important. Uniform does not mean normal. Uniform just means it goes straight across for those values. So in essence, it's like you're working with a rectangle. So in this case, it says the amount of time that workers at a factory spend in training each month that follows a uniform distribution between 0 and 7. So what we've got here is our numbers are varying from 0 to 7. So let's say it goes, and I'll go ahead and mark these 1, 2, 3, 4, 5, 6, 7. I'll go ahead and label those 3, 4, 5, and it's even. It goes straight across. It makes a little rectangle. And so every value in the rectangle here represents the time they spend in training. So one guy spends, 2.356, another person spends 4.987. So all these points represent those times. All right, and so it says if you randomly select a worker, what's the probability they spend greater than 5 hours? So greater than 5 hours would be everything greater than 5. And so with a continuous curve, there can be kind of different ways of thinking of this, but the probability that x is greater than 5, I just want to calculate this. It is going to be the area of a success, as we call it. And in this case, be greater than 5 would be what we kind of call a success, over the total area of our curve. And I like to just make the height of this rectangle 1. And so the area of a success is greater than 5. And so what's the area here? Where it's 1, 2 times 1. So the area that's greater than 5 is 2. What's the total area of this rectangle? Well, if you count over 1, 2, 3, 4, 5, 6, 7, it's 7 long and the height is 2. So the area of that rectangle is 7. So if you were to randomly select a point in this rectangle, the probability of being in this shaded area would be 2 out of 7. Right, like that. Then it says, well, what's the probability that it'd be greater than or equal to 5? In other words, what if we added on this value above 5? And with a continuous curve, it's not going to matter. It's still going to equal 2/7. Because even though you are adding something, you're adding something that has no area, because the area of this line segment is 0. So in a continuous distribution, greater than something is the same as greater than or equal to something. Same thing with less than or less than equal to. Now that's different in discrete random variables. Discrete random variables, greater than 5 is different from greater than or equal to 5. All right, so and then it says this. We've got this conditional problem. If you randomly select the worker, what's the probability they spend greater than 5 hours given they spend greater than 3? So we've had those last chapter, the probability that x is greater than 5, given that x is greater than 3. And this is the way we're going to handle conditionals in this chapter. It is in essence going to be the area that is greater than 5 over the area that's greater than 3. Last chapter, the little formula said, well, it's the probability of both of those things over the probability of the second one, and that's the same thing. I mean, to say something is greater than 5 and greater than 3, the easier way of saying that is just saying it's bigger than 5. If something's bigger than 5 and it's bigger than 3, it's just bigger than 5. So what is the area bigger than 5? Well, we've already found that. The area bigger than 5 is just 2. What's the area bigger than 3? Well, the area bigger than 3 would be 1, 2, 3, 4. So if you were to randomly pick a point that's bigger than 3, what's the probability to be bigger than 5? It would be 2/4, or just 1/2. So that's, uniform, different uniforms problems. People tend to do pretty well on that. Once again, don't think that that's normal. So then we have our normal problems. Most of this we already did in Chapter 2, so you should be familiar with it. There's kind of a couple of new twists here that I wanted to remind you about, and just wanted to remind you just how you properly show your work and that sort of thing. So in this sort of thing, it says we have a standardized test that's given to 7,814 fifth graders in Detroit, Michigan. The scores follow an approximately normal distribution. So we think all those things that we learned in Chapter 2. With a mean of 8.3, standard deviation of 2.1. If you randomly select one of the students, find the probability the score will be less than 5. And so in this case, it's asking us to draw the curve, show the shading, and find the proper z-score. So I'm going to draw this curve right there, and anytime I draw a curve, I label what it is. This is normal, and it says the mean is the measure of centers, 8.3, right there in the middle. All right, and then the standard deviation is 2.1, so I just kind of say sigma is 2.1. But if that means if you go up one standard deviation, it's going to go basically halfway down this hill to that inflection point, as we call it. And so that would be plus 2.1 to be 10.4, and then one standard deviation below it would be to this inflection point, basically halfway down that hill. And so that would be 6.2. So I just labeled it 1 and 2 one standard deviation above and below the mean. And then it's saying if you randomly pick a point in this curve, what's the probability to be less than 5? Well, 5 I'm just going to estimate to be about right there. And so I need to know this area of this right here, this less than 5. And so what we would do is we would find the z-score. So the z-score, you recall, is the x value, 5, minus the mean over the standard deviation. It is just a measure of how many standard deviations your x value is from the mean. So it's x minus mu over sigma. And so when I do that, this gives me negative 1.5714 approximately. We could then go to Table A, and we call Table A. Table A tells us the area that's below a certain z-score on a normal curve. And we notice z-score here, go down to negative 1.5, and then go over to the 0.07 column. We'd have to round to there, so this is just an approximation. And that would take us down to 0.0582, and so that would be our answer. So our area on Table A is approximately equal to 0.0582. Boom. There we go. And that would be how you do that using the table. Now, using your calculator, using your calculator, we'll use the function normal CDF, and I'll remind you about that. And our left bound is negative infinity here because it goes on forever, so that's our lower bound. We say LB for lower bound. UB for upper bound is 5 of my shaded region. Then remember the mean, we label the mean 8.3 with a mu, and then a sigma of 2.1. If you forget those symbols, you can just write the word mean and standard deviation there. And so let's see what we get. So let me remind you that the normal calculations are right there above the VARS button in distribution. So if I go second VARS or distribution, go to normal CDF. So negative infinity, or you could just put negative 10,000. Make sure and put the negative sign, not the minus sign. That'll mess you up. So negative infinity to 5. That's my lower bound, and the upper bound of my shaded region. Mean is 8.3. Standard deviation is 2.1. And so that gives us equal to 0.05804. It's actually a bit of a more precise answer than the one off the table, but that's how you do it. Now, technically, on the AP Stats exam, if you just if you just wrote this, you would get full credit for showing your work. All right, be essentially correct if you said normal CDF, if you clearly labeled what these were with a mu and sigma, lower bound, upper bound. All right, but you certainly could be asked to show your work in this way by drawing the curve, showing the proper shading, and finding the z-score. So that is a frequent question, so you have to understand how to show your work, and I'll certainly ask you to do that from time to time. Then what's the probability, the next one, that it's going to be between 6 and 10? If you randomly pick a point, on this curve, what's the probability to be between 6 and 10 to be in there? So that's another normal CDF problem. Normal CDF tells us the area in a normal curve. So my lower bound is 6, so I go LB for lower bound. My upper bound is 10. My mean is 8.3. My standard deviation is 2.1. So that's my mu and that's my sigma. And so let's do that. And so I will go to second distribution, normal CDF from 6 to 10, mean of 8.3, standard deviation of 2.1. And so we get 0.6542 approximately. Approximately equal to 0.6542. Good idea to use at least 3 or 4 sig figs. There we go, about 65% of the curve in essence. All right, and this is a little different than what we did in Chapter 2. It's a little bit of a new twist. It's a conditional probability like we did last chapter. All right, what's the probability that you're going to get a value greater than 11 given that it's greater than 9? Okay? In other words, if on this curve, if you randomly select a value that's, let's say 9's about right here. If you randomly select a value that's bigger than 9, what's the probability it's going to be bigger than 11? Okay, and that's what this is telling us. And the way you do this is by saying, well, that's going to be the area that is greater than 11 over the area that is greater than 9. Well, how do you find the area greater than 11? That's normal CDF. So we'll use that same function, normal CDF from 11 to infinity, mean of 8.3, standard deviation of 2.1. Label this lower bound, upper bound, mu and sigma, always label it. And then, once again, to find the denominator, normal CDF from 9 to infinity, mean of 8.3, standard deviation of 2.1, mu, sigma, lower bound, upper bound. And so when you find these values, let's see, you get, I believe, 0.09927 for the numerator, and then greater than 9 ends up being 0.36944. And so that ends up being 0.2687. And so there we go. So that is that calculation. All right, what value is smaller than 30% of values? Now, if you think about that, so in the normal CDF, it gives you the area. The answer in these normal CDF problems is the area of the curve. But in this one, it gives you an area. And so this is an inverse norm problem. So it's saying what value is smaller than 30% of values? Okay, now, in most TI, and a lot of the older TI-84s, it only works with a left area, so that's what I'm going to do, and it's kind of what I'm in the habit of doing. And so what it is this, is if value is smaller than 30% of values, that means it's got to be bigger than 70%, which means this is the 70th percentile. And the way you find percentiles in a normal curve is inverse norm. And so I will show you that function again. So we say inverse norm of 0.7. You label that as left area. And then our mean, once again, is 8.3. Standard deviation is 2.1. We've only got 3 parameters here, so this is mu, and that's sigma. All right, let's go to that, okay? The inverse norm is right below normal CDF. It's in the distribution menu right above the VARS button, so I go second VARS distribution. There it is. Inverse norm. And so the area is 0.7. That's the area to the left. Mean of 8.3, standard deviation of 2.1, and it's the left area. Now, this is one of the modern 84s where I could have gone right area actually of 0.3, but I'm just going to go left area of 0.7. And so, so it ends up being that. So those are the parameters you enter, because some 84s take you directly to this menu, which would be 0.7, 8.3, 2.1. We hit enter, and it's 9.401 approximately. 9.401. Then you always ask yourself, does your answer make sense? And so if you go back and read the problem, if a value is smaller than just 30% of values, that means it's above average. The average here is 8.3. So if it's smaller than the 30% of values, it's the 70th percentile, you're expecting it to be bigger than 8.3, and it is. So sometimes it's easy to kind of get this mixed up with your percents and accidentally find the 30th percentile, but just sort of look at it and see if it makes sense in the context of the problem. Now, these next, this problem here is one of the more involved problems we have really all year, and it's something we did in Chapter 2, but I wanted to remind you of it because it is a popular problem, and that is, first of all, finding the IQR and then the outliers. Remember, the IQR, very popular question, It's Q3 minus Q1. It is a measure, one of our main measures of spread along with standard deviation and range. And it is just tells us what the middle, how the middle 50% of values are varying, which can be an important thing for us to know. Q3, the upper quartile, it's the 75th percentile. Q1 is the 25th percentile. And so how do you find percentiles in a normal curve? Inverse norm. So I'll do inverse norm of 0.75, mean of 8.3, standard deviation of 2.1. So that is my left area. That is my mu, and that is my sigma. That is Q1. That is how you find Q1. All right, and then minus Q1, that's Q3. 75th percentile, that's Q3. Now I find the 25th percentile, which is Q1. So inverse norm 0.25 so that is my left area. And then this is 8.3, this is 2.1. That is my mu, that is my sigma. And so when you find these things, it ends up being, let's see, 9.7164. So this right here ends up being 9.7164, kind of running out of space here. And then minus, and then this ends up being 6.8836, to where the IQR is 2.833. That is our IQR. And that's how you find the IQR, Q3 minus Q1. Now let's find the outliers. So hopefully I've got enough room here to find the outliers. Remember from chapter 1, outliers are anything that is greater than Q3 plus 1.5 times the IQR, or less than Q1 minus 1.5 times the IQR. These are values that in general fall outside the pattern of the other values. So let's find the high end ones first. And so you just plug in these three numbers here that we, Q3, Q1, and the IQR. So this would be 9.7164 plus 1.5 times 2.833. And when you do that, you would say, well, anything greater than about 13.96 would be classified as an outlier. Then what about on the low end? Well, Q1, so that would be 6.8836 minus 1.5 times 2.833. And so anything less than 2.634 would be an outlier. And so outlier is anything greater than that, anything less than that. So, for a normal curve, sort of a shortcut that you can use to check. Now, this is properly showing your work as far as an outlier, and that's what you have to do. That works for any distribution, by the way, not just normal curves. But in a normal curve, an outlier is 2.7 standard deviations above or below the mean. I really don't encourage you using that, but it is a way you can sort of check your work. If you said 2.7 times that and added it to that, it should be approximately equal to that. Okay? And if you said 2.7 times that and you subtracted it from that, it should be approximately that. So that only works for the normal curve, and that's not considered showing your work on that. So this is the only way you really need to know. So I actually sort of hesitate to even tell you the 2.7 thing. But you have to know this. Please know this. Then lastly, this. And so how many fifth graders had a score greater than 10 on the test? And well, we have a total, it says up here, there's a total of 7,814. So that's our total, 7,814. So it made greater than a 10. Well, we can find the proportion that are greater than 10 by doing normal CDF. That's what we've been doing up here in parts A, B, and C with these calculations. We've been finding the area or the proportion. And so we'll say normal CDF, so greater than 10, so that'd be 10 to infinity, and a mean of 8.3, standard deviation of 2.1, label them as lower bound, upper bound, mean, standard deviation every time, and so that ends up being 0.209107. So that's saying roughly 21% of these kids made above a 10, 20.9%, let's say. And so how do we find 20.9% of that? Well, we multiply that, and so we'd say 7,814 times 0.209107. I like to use a healthy number of significant digits here so we can get, pretty accurate answers. And so that ends up being 1,633.96. And so we would say 1,634 students is what we would say scored greater than a 10. Okay, thank you very much for paying attention. I wish you all the success in the world in regards to continuous random variables.